Hello everyone, I'm Qingguo from Dr. Jeremy Levy's group, University of Pittsburgh. My topic is Coulomb drag between graphene and lanthanum aluminate strongly tightened heterostructure. Coulomb drag is a direct way to study the interactions between charge carriers. Drag experiment involves two closely spaced but electrically isolated conductors. In such a system, an electric current flowing through one layer, which is called drive layer, will introduce a voltage on the drag layer. By this method, one can study the scattering between charge carriers belonging to different layers due to long-range interactions. These scattering events are accompanied by momentum transfer and energy transfer. A lot of pioneer work was done in aluminum gallium arsenide double quantum well. As an example, in 2012, perfect Coulomb drag is observed in this double quantum well due to the existence of exciton condensates. Recently, more and more experiments are done in double-layer graphene system since graphene can allow one to tune the carrier density in a wide range and it has less disorder strength. In 2017, exciton condensate was first reported in double-layer graphene system. Recent measurements of Coulomb drag in double-layer graphene system show strong drag signal with unusual density dependence was attributed to the energy transfer due to the proximity of graphene layers. Coulomb drag is also studied in hybrid devices, for example in graphene gallium arsenide heterostructure. Due to the strong interlayer in correlation, the ordinary quadratic temperature dependence expected in a weakly correlated Fermi liquid doesn't apply. In our group, we are mainly focused on one 2D material, lanthanum aluminate strongly tightened. Lanthanum aluminate, which strongly tightened, which we call them shortly for LaLO, contain almost all the major tuning properties in solid-state physics, such as superconductivity, ferromagnetism, ferroelectricity, spin-orbit coupling, and so on. Both LaLO and SrTiO are insulators, but when we put them together, a 2D electron gas can be formed at the interface when the thickness of LaLO is above 4 unit cell. This metal insulator transition can also be tuned by applying a backgate. More interestingly, with the conductive c-AFM lithography technique invented by our group, we are able to write nanostructures at LaLO-SrTiO interface. This animation will demonstrate an example of the writing and erasing process. First of all, we apply a positive voltage on the AFM tip and write two triangular shaped patterns, which we call them virtual electrodes. Those will help to form robust electrical contact to the oxide interface. Then also with a positive voltage, the tip is scanned from one electrode to the other. In this way, we can create a connecting wire between these two electrodes. If we apply a negative voltage on the tip and move it across the conducting wire, we can create an insulating gap in between. Our goal is to integrate these two novel systems together. So we put graphene directly on top of LaLO-SrTiO and pattern graphene into a hot-bar structure. And then we contact the graphene and LaLO-SrTiO by fabricating the gold electrodes. Here is an AFM image of the device, and we did room temperature STM, which shows our device is atomically clean. And here is the transport measurement done at 2 Kelvin. We can see the quantized plateau of graphene at 2, 6, 10, etc. The mobility of graphene can be as high as 30,000 at 2 Kelvin. So here comes the question, can we still write nanostructures with graphene on top of LaLO-SrTiO? The answer is yes. So here we designed a pattern that we have two triangular shape conducting region and one nanowire that go across the graphene. So after the writing, we see the conductance jump between these two electrodes, and from a PFM image, we can see that the that the wire is it looks exactly the same as we designed. With this writing technique, we started to fabricate our Coulomb drag devices. So here is a graphene hotbar structure, and then we apply positive voltage to the AFM tip and write a conducting region that underneath the graphene, and then we connect this rectangle region with to the SrTiO interface electrodes to make contact, and then we measure the leakage between the graphene and this green conducting region. So as we can see, if we keep the voltage between graphene and SrTiO to be smaller than 200 millivolt, the the leakage current is very small. So we can perform the Coulomb drag experiment between graphene and LaAlO SrTiO. First, we start running the current in graphene and measure the drag voltage in SrTiO. We plotted the drag voltage as a function of magnetic field and the carrier density in graphene. As we can see, the drag resistance is enhanced near the zero magnetic field region, and this is the corresponding voltage in graphene measured at the same time. Then we run the current in SrTiO and measure the drag voltage in graphene. We can see these stripe-like features as we change the carrier density in graphene. And this is the voltage we measured. This is the SrTiO voltage measured at the same time. So if we correspond these four figures together, we can see the drag signal in SrTiO is greatly enhanced when the SrTiO is in a superconducting region, and also this stripe-like features is very similar to the resistance in graphene. Then we measure the drag signal as a function of the driving current. So right here we are changing the current strength in the graphene and measure the drag voltage in SrTiO as a function of the driving current. We can see the signal is greatly enhanced at zero magnetic field, which corresponds to this drag signal enhanced as a function of the carrier density. And if we go outside the superconducting region, the signal is greatly suppressed. Then we try to study the drag signal in graphene in a much larger magnetic field region. So in device 2, we still got the stripe-like features, which is very similar to the first device, and then we scan the signal in a much larger magnetic field up to 9 Tesla, and we can see this two parabolic shape of the outline of the drag signal. So we can see the signal is more obvious in the high magnetic field region and low magnetic field region, but not in the intermediate magnetic field. To better understand that, we did a Kwant simulation on graphene. Kwant is an open source Python package for numerical calculations on tight bonding models with a strong focus on quantum transport. Here we employ the Kwant software to calculate the conductance of graphene device. Two graphene leads are attached to the graphene and try to obtain the conductance of graphene. And our device is depicted here. The honeycomb lattice has two basis atoms. A potential wheel is added to graphene in the center as shown here. The height of the wheel is 0.3 eV. And here we put the density plot of wave function at some fixed chemical potential, and we vary the magnetic field. So we can see at 0 Tesla, the wave function is distributed in the whole device, and as we increase the magnetic field, the wave function is localized at one graphene lead. And as we keep increasing the magnetic field, edge states start to form, so the conductance can exist from one lead to the other, which corresponds very well with our experimental data. So here we plotted the conductance as a function of magnetic field and Fermi level. So this is the result of Kwant simulation, and this is the experimental result. We can see that both of them show the conductance in the low and high magnetic field region, but not in the intermediate region. So if we make the assumption that the momentum is transferred from SrTiO carriers to graphene carriers through one collision, we can see that the transport properties in the drag layer is mostly following the tendency of the drive layer. We also studied the Coulomb drag in Hall and longitudinal direction. So here we run the current in SrTiO and measure the drag voltage in graphene. If the drag voltage is measured parallel to the driving current, the drag signal is more obvious in the low magnetic field region, and if the drag signal is measured perpendicular to the current, we can see the drag signal is more obvious in a high magnetic field region. And this is also true if we change the current in the we measured in graphene. So we're running the current in graphene and measure the drag voltage in two directions. One is parallel to the driving current. We can see the drag signal is almost symmetric under a positive and negative magnetic field. And if we measure the drag voltage in a direction perpendicular to the drive current, the drag signal is antisymmetric under magnetic field. For a short summary, conducting region can be created by conductive AFM lithography technique and imaged by PFM. In a high magnetic field region, drag resistance is observed to be magnetically tunable, and drag signal is greatly enhanced in SrTiO superconducting region.